Welcome back to our third lesson in our thermodynamics unit. Today we are going to be looking at calculating enthalpy through a process called Hess's law, where we're adding reactions together, multiple steps, to determine the enthalpy of a reaction that is the sum of those other reactions. So, when a reaction can be expressed as an algorithmic sum of two or more reactions, its heat of reaction is algebraically the sum of the heat of the individual reactions that were added together. So if we look at our first example here, we've got reaction number 1 is sodium hydroxide dissolving in water, so going from solid to aqueous. Then we're using that aqueous in reaction number 2. We're adding hydrochloric acid to form sodium chloride and water. And reaction number 3, is a sum of these two, in that you'll see we're looking at sodium hydroxide solid reacting with our hydrochloric acid, and we're getting rid of this intermediate step. So we're taking that and that, we're getting rid of those. We're going to add those two together to give us the enthalpy of our target reaction, reaction number 3. So here, reaction number 3 is a sum of reactions 1 and 2. Therefore, if we take our delta H from 1 and from 2 and we add them together, that will give us the delta H of reaction 3. Now, when you manipulate equations, now we've done a bit of manipulating equations before, but I know it was a long time ago, it feels like. So it works very, very similarly as we did before. If you flip a reaction, then you have to change the sign. So if it's positive, it becomes negative. If it's negative, it becomes positive. If you multiply a reaction by a number, so either multiplying by 2, or if you're multiplying by a half, which is dividing by 2, then you have to multiply your delta H value exactly the same way as you multiplied your reaction. And then when you add your reactions up together, you add your delta H values together. So in the past, we done multiplication, but now we're just add. So let's jump right into an example. So here is our target reaction. Determine the heat of reaction of looking at carbon and hydrogen making ethyne, so C2H2. We have 3 reactions here with delta H values given, but we want to find the delta H of this target reaction. So we're going to have to change these around, maybe move some stuff, maybe flip some things, to be able to cross out sort of spectator intermediates and get our final target equation. We'll manipulate our delta H's as needed, and then at the end add them up to get the delta H of our target reaction. So this is our target that we're trying to get to. Now, the strategy that I like to use when I'm doing these is I look at this reaction, I say, how do I get that? And then how do I get that? And then how do I get that? So here, our first piece is 2 carbon solid. And so I'm going to look at my other reactions that I have options of, and I'm going to find this molecule. So the only place it appears is in reaction number 2, where we have carbon solid plus oxygen making carbon dioxide. So that's the one that I'm going to deal with first. So I'm going to bring it down and I'm going to rewrite it because I do need to change some things about it. Here, we only have 1 carbon, but in our target, we have 2 carbons. So we're going to need to multiply this whole reaction by 2 to help us get our target. What that will look like then is 2C solid plus 2 oxygen gas making 2 carbon dioxide gas. Now remember, anything that we change about our equation, we have to also look at how it's going to change our delta H value. So now the new delta H for this reaction is going to be equal to 2 times the original, so that negative 393.5. So we're going to multiply that by 2. That's going to give us negative 787 1.0 kilojoules. So that's our first one. Now let's go back to our target and see what else we need. We also need, on the reactant side, we need one hydrogen molecule. So the only place that we can find hydrogen in our other equations that we're using is the third one. So here is our hydrogen. We're going to use that one next. We're going to add it below and rewrite it. When we look here in this equation, we have 2 H2, but we only want 1. So we need to change this equation by either multiplying it by half, or you can divide by 2. I find it a little bit easier to think about it as dividing by 2. So dividing by 2 would give us H2 gas plus 1/2 O2, giving us 1 H2O liquid. Now our delta H for this one was negative 571.8, but we divided it by 2, so we're going to take negative 571.8, and we're going to divide it by 2, just like we divided everything else in this equation by 2. That's going to give us negative 285.9 kilojoules. Now our last piece here, we know we're able to find this, we know we're able to find this, but we also need this C2H2 molecule. The only place that C2H2 is in our equations that we get to manipulate is in the first one, but it's on the wrong side. So over here, it's a product, and here, it's a reactant. So we need to flip this whole equation to get it on the other side. So I'm gonna bring this one down third, and I'm gonna reverse it. Now in this case, I only have one C2H2 here, and I only have one C2H2 here, so I don't need to multiply or divide this reaction by any number, but that could happen. It could be that you have to reverse and multiply by something, but in this case, we're just reversing. So I'm gonna write it in the opposite order, so I'm gonna have water and 2 carbon dioxide on the reactant side now, and C2H2 and 5/2 oxygens on the product side. And for this one, we need to reverse the symbol. Okay, change symbol. Oh, sorry, I'm pointing to the wrong one. We're working with this one. There, change symbol, because we reversed it. So delta H for this one is now positive 1299.6 kilojoules rather than it was negative originally. So now we get the fun part of crossing all kinds of things out. We're going to actually add these reactions together and make sure that we can get our target equation. So carbon solid, it doesn't appear anywhere else here, so it's not going to cross out with anything. Hydrogen gas, it also doesn't appear anywhere else, so it's not going to cross out with anything. Water is both on the reactant side and the product side. Oh, this pen doesn't really want to work. There we go. So we can cross it out. We have one here and we have one here, so they're going to cancel each other out. Next, we also have carbon dioxide on both sides of the arrow, so it's also an intermediate that's going to be produced and then used up. So 2 CO2 here, 2 CO2 here as well. There's 2 of both of them, so we can just cross both of those out. And our last thing that's on both sides of the arrows is oxygen. So here we have 5/2 oxygens. Here we have 2 oxygens and a half an oxygen. You might find it helpful to think of this 2 as like 2/1. Any number is technically over 1. And what we can do is we can also write that out as 4/2 to have all of our fractions over 2 to make it easier to count them up. So that would give us 4 plus 1 is 5. 5/2 oxygens when you add both of those up. And then 5/2 oxygens on this side as well, so we can cancel all of these out as well. Then we're going to carry down past this sort of line here, only the stuff that is not been crossed out. So that's our 2C solid plus our hydrogen gas, and that's going to make our C2H2 gas. And everything else has been crossed off. Our delta H is going to be the sum of our 3 delta H's of our reactions. So that's going to be a total of minus 787.0 plus negative 285.9 plus positive 1299.6 is going to equal a total of 226.7 kilojoules as our final delta H for our target reaction. All right, we're going to do one more example together. If you feel like you need a quick break, you can pause the video and take a quick stretch, maybe wander outside or open a window if it's nice, and then come back and do one more practice question before you try the clock. Okay, example number 2. Calculate the delta H for the following reaction. So now this is our target reaction. And we want to find delta H in kilojoules for that particular reaction. We're given 3 other reactions with known delta H values that we can use to find this one. So first, look at what is this first piece. It's ammonia, NH3. So we're going to look in our equations and see where do we see NH3. The only place we see NH3 is in the first reaction, and there's 4 of them, but we only want 2. So we're going to use this equation first, but we're going to divide by 2 or multiply by half because we only want 2 NH3, not 4 NH3. So when we divide this by 2, that's going to give us 2 NH3 plus, it's easiest to just write this as a fraction because it's 5, so 5 over 2, O2 gas. Then 4 divided by 2 is 2 NO, and then 6 divided by 2 is 3 H2O. And our delta H for this reaction, I highly recommend that you calculate your delta H's as soon as you manipulate an equation. Don't do it like at the end when you're trying to figure out, oh yeah, what did I do to that equation? Just do it right away and write it down. It makes the last step a lot easier. So we divided this whole reaction by 2, so we're going to divide our negative 906.4. We're going to divide that by 2 as well to get negative 453.2 kilojoules as the delta H for this new reaction. So now we figured out where we're going to get our delta H from. We are going to be adding oxygen, but something that's tricky about this is that if you do oxygen next, you'll notice in here there's oxygen in a lot of places. And when there's a piece of the puzzle that's in multiple locations, it can be a lot harder to see what you need to do. So I would recommend doing it last. So yes, there's oxygen sort of next in line, but because it's in so many spots, I'm going to leave it to the very end, and that'll be a lot easier to deal with. So I'm going to go to the next piece, which is this N2O, and I'm going to see where is N2O in my reactions that I'm using. And the only place it appears is in reaction number 2. So I'm going to skip oxygen, move right on to the dinitrogen monoxide. Now the dinitrogen monoxide, move that one down. We only want 1 in our target, but here we have 2, so we're going to divide by 2. It's also on the wrong side of the arrow. So here it's on the reactant side, but over here it's on the product side. So we need to divide by 2, and we need to reverse it to flip it over. So when we reverse and divide by 2. That's going to give us, so this is now going to be our reagent. Divide the 4 by 2 will be 2NO2. And then we've got oxygen divided by 2 will be 3/2 oxygen gas and 1 dinitrogen monoxide gas. Our delta H, we need to flip the sign, so we're going to make it positive, and we also need to divide it by 2. So I'm gonna just flip the sign and make it positive 27.0, and I'm gonna divide it by 2. So that's going to give us positive 13.5 kilojoules for that reaction. Last thing here is water. Now you'll notice that water is only in our first equation. We already have the right amount of water here. So the only thing left to figure out is the oxygen. So now we have to figure out how do we change this final equation to cross out stuff that we need to cross out and end up with a correct amount of oxygen. So this one's a little bit trickier than the last one. When we bring this down, we have to think about what do we need to do to it, if anything, to get rid of stuff that we don't want. Okay, so stuff that we don't want are those intermediate molecules that are here, but they're not anywhere in this target equation. Okay, so some of those are things like nitrogen monoxide. Okay, it's not here anywhere, but it's here in a couple places. We want to get rid of that. Another thing that's not here but is over here is nitrogen dioxide, so NO2. That's another molecule that we want to get rid of because it's not actually anywhere in here. So when we're looking at how we've manipulated our other equations, we can see we want to be able to cross out this 2NO2. We also want to be able to cross out this 2NO. Looking at our final equation here, we want to make sure we have those same pieces, which we do, and that they're on opposite sides of the arrow as they are in the equations we've already manipulated. So this one we actually don't need to change at all. Okay, so we're not going to do anything to it. So nothing. It is good the way that it is. So we'll write it out, 2NO gas, okay, which will allow us to cross that one out, plus O2, and then making 2NO2, okay, which will allow us to cross that one out. So our delta H for this one, we didn't do anything to it, so it's still going to be negative 112.8 kilojoules. We don't change that at all because we didn't change the equation. Now let's cross stuff out, add stuff up, figure out what our delta H is. So first, that's good the way it is. Oxygen, leave it to the end because it's in so many places. 2 nitrogen monoxide. So this isn't in our target. We want to get rid of it. We also have 2 nitrogen monoxide down here. So we're going to cross those out. Then we also have 2 nitrogen dioxide. Nitrogen dioxide isn't anywhere in our target. We want to get rid of it. There's 2 on this side of the arrow, and there's 2 on the other side of the arrow in this reaction. So we'll cross that one out. And the last thing is just to add everything else up. Now, our oxygens are a little bit complicated here because we have some oxygens on one side of the arrow and some on the other side of the arrow. We want to hopefully end up with 2 oxygens on the reagent side. Again, oxygens are the most complicated one in this one, so we're just going to leave it to the very end. We've got 2 ammonia. It doesn't exist anywhere else, so I know I'm going to write it out. 2NH3 plus some amount of oxygen, hopefully 2, but we'll double check that at the end. And we're going to end up also with our N2O. This doesn't have anything else anywhere else, so that one's good. And our water, there isn't water in any other spot, so plus 3H2O is good. And now let's figure out these oxygens. So we've got 5/2 oxygens here, we've got 3/2 oxygens here, and we have 1 oxygen here, which I would consider writing it as 2 over 2 so that all of your oxygens are in fractions of the same terms rather than thinking about it as like one whole. So we have 3 here. We can subtract it from those 5 to make 3, sort of 5 minus 3 gives us 2, and that will use up the oxygen that's on the wrong side of the arrow. So that gives us 2 over 2. So 5 over 2 minus 3 over 2 gives us 2 over 2, which is equal to 1. And this one is also equal to 1. So that's 1 and 1 gives us a total of 2 O2 gas. So now double check, does this match our target equation? Yes, it does. Our delta H, we need to add up our delta H's from our other equations. So the first one was negative 453.2 kilojoules, plus the next one was positive 13.5 kilojoules, plus negative 112.8 kilojoules will give us a sum of negative 552.5 kilojoules as our final delta H value. So that's it. You have some textbook practice questions listed at the bottom there to do for practice, and I will see you guys later.